My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 220. In this lecture, we will try to understand a simple, straightforward concept known as mean of data matrix. So let's assume we are given a data matrix. We have a data matrix, isn't it? Where each column is a feature. Let me assume these are the features F1, F2, so on, Fj, so on. I have D features. Fd are the features, and each row corresponding to a point. Let me write this data matrix which we were discussing about this from few classes. I discussed in my previous classes also. Just let me assume 1, 2, 3, so on. I can say this is ith data point. So on, let me say this is nth data point. This is F1, feature 1, feature 2, feature 3, so on. Let me say this is feature J, this is feature D. As there are D features, how many rows? There are n rows and D columns. It's n by D matrix. I can say, how can I represent my ith row as by default xi is a column vector, xi transpose is a row vector. What is my jth feature? This is Fj is known as my jth feature, which we already discussed this one, isn't it? It's not a new thing, isn't it? Ith data point. What is my ith data point? My xi is the ith data point. And what is my jth column? My jth column, I can say this is jth feature. Column means I can say it is jth feature. What is my jth feature? That is Fj, isn't it? That's jth feature. This is our standard practice of representing a data matrix. So each of your xi, each of xi belongs to Rd, means d-dimensional. Basically, it is a column vector. Xi belongs to Rd. So if I compute mean vector as follows, what if so? Suppose if I have two vectors, let me say x1 equal to, let me say 2.2 comma 4.2. This is my first vector, and my x2 is equal to, let me assume this is 1.2 comma 3.2, isn't it? This is in x1, this 2.2 is feature 1, this 4.2 is feature 2, whereas in x2 this 1.2 is feature 1 and 3.2 is feature 2. Now how can I calculate x1 plus x2? x1 plus x2, this you must remember. Here your x1 belongs to R2, isn't it? In similar manner, your x2 is also belongs to R2. Now what I need component wise addition. X1 plus x2, that is 2 plus 1.2, that is, it is essentially 3.4. Again component wise addition, 4.2 plus 3.2, that is 7.4. Isn't it? It is simple, straightforward. This is sum of two vectors. This is component wise sum. So mean of vectors. Suppose what if I compute x bar? How can I calculate my x bar? Let me say x belongs to x bar is essentially, I can write 1 by n into sigma I equal to 1 to n, isn't it? Xi, isn't it? This one, what I am doing, I'm doing component wise sum, and I'm taking average. X bar is called mean vector. I can say this vector x bar is a mean vector. I can write this x bar as x bar is equal to 1 by n into x1. If I keep I equal 1 x1 plus I equal to x2 plus so on, I can say I equal to n xn, x1 plus x2 plus so on xn by n. Again here, each of, you must understand, each of xi belongs to Rd. Isn't it? Means your x1 belongs to Rd, your x1 belongs to Rd, your x2 belongs to Rd. Isn't it? In similar manner, your xn belongs to Rd. All these are vectors. X1 is a vector, d-dimensional vector, x2 is a d-dimensional vector, and so on. Xn is also d-dimensional vector. Then what is your x bar? Your x bar is also belongs to, it is also d-dimensional vector. What does it mean geometrically? Let's understand geometric interpretation of a mean vector. Imagine, just imagine, let me say like this. Imagine I have two features. Let me say like this. Let me, otherwise I will repeat. What does it mean geometrically? Let's understand geometric interpretation of mean vector. Imagine if I have two features. Again, we will always understand it in two dimensions. Let me say this is my feature 1, this is my feature 2. Let me assume my feature 1 is height and my feature 2, let me assume it is weight. Let it be weight. Let's assume each of them are my points. Just let me say this is my points, these are my data points. I can say like this, these are my data points. I may have some sort of data points. I am collecting data related to heights. I am choosing heights on x-axis and corresponding weights on y-axis, isn't it? This may be the pattern. Let me assume I have data points. I have data points like this, isn't it? It's simple and straightforward. Just for simplicity, let's assume these are heights on x-axis. I'm taking heights, and these are weights on y-axis. I'm taking weights, isn't it, student? For simple, so for each xi belongs to R2. Each xi belongs to R2. The first one is height and second one is weight. I can say this is H1 comma, I can say H comma W. It is H comma W. My H is feature 1, my W is feature 2. Isn't it? The first feature, this is my first feature. My first feature is height. My first feature is height. My second feature is weight, isn't it? So what does it mean? What does it mean? Vector represent. So what does mean vector represents? We will try to understand what does mean vector represents. What is the geometric interpretation of mean vector, isn't it? So what does mean vector represent geometrically? If I project all of these points, let me say if I project all of these points, if I project all of these points on x-axis, I can say if I project all of these points and compute f1, let me project all of these points on x-axis and let me compute f1. F1 means feature 1 or feature 1. F1 means what? I'm computing feature 1. Feature 1 for this you will have this value. So if I project all of these points on x-axis, now I have scalars. I have what I have? I have heights, isn't it? I have basically heights of students. If I project feature 1 on x-axis, I have feature 1. I on x-axis I can have heights of the students, isn't it? For the mean vector x bar, what I have to calculate? I must say simply, I can say my x bar is equal to, I must compute mean of all heights and I must also compute mean of all weights. What is this hx bar? What is the meaning of hx bar? Hx bar is essentially, mean of, I can say mean of hi. Let me say mean of hi, I equal to 1 to n. I'm collecting all heights and I'm calculating mean of all heights and keeping in hx bar. In similar manner, what is my wx bar? I must calculate. What will I calculate? Mean of wi, isn't it? Mean of wi, I equal to 1 to n. What does it mean? hx bar and wx bar. Hx bar is mean of, I can say mean, this is mean height. I can say it is mean height. In similar manner, I can find mean weight. This is, I can say this is mean weight, isn't it? Now I have mean height because what are we doing? Geometrically, a mean vector is just like for scalars. What does mean represents? So far, for example, for all those values, let's assume mean is here. Mean is a sort of central value. I can say mean can be treated as, mean is some sort of central value. It is some sort of central value, isn't it? I already discussed in my statistics classes, mean is one of the central tendency, isn't it? It is a central tendency, isn't it? I can say it is central value, isn't it? Mean, I'm calculating central value for heights and I'm calculating central value for weights. Therefore, I can say geometrically speaking, mean vector is a sort of like central vector. That you must understand. Mean vector is central vector. This point is important. Let me write here. I can say this is central vector. Mean vector is a central vector. Central vector means, geometrically speaking, mean vector is a sort of like central vector or central data point. So geometrically, mean vector is nothing but a central vector. Here I can say this may be the central vector. If I take mean of all these heights and weights, I may get this some sort of central vector. Just like mean is central value for scalars, mean vector is a central vector. So that's the interpretation of mean vector. We will also see other things like covariance of data matrix. Not only covariance of data matrix, in my next lecture I will discuss about a concept known as, there is a concept known as column standardization. What is this column standardization? We will try to understand in my next lecture. Just time being, just go through this mean of the vector. It is simple. I can say mean is a central vector. You may have some vector, central sort of vector like this. Just geometrically try to understand this one, and I will continue my discussion in my next lecture, that is in lecture number 221. In lecture number 221, as I told you, I will discuss about a concept known as I can say column standardization. I can say standardization. I will discuss this particular concept in my next lecture. This column standardization, it is a part of data pre-processing. It is a part of data pre-processing. You can treat it as a part of data pre-processing. Thank you very much.